deep learning. So as I said, that we don't really need you to have like a deep knowledge about deep learning, because I'm gonna have 3 hours really about that subject. So today is I will have a very quick overview about what is learning in general, and this particularly machine learning around deep neural network. And so I, in fact, have quite a lot of slides to go through. Therefore, my explanation might be very quick, but I have quite comprehensive slides for you to start study. So I think you could, if you're not really studied the deep learning in the past, then this certainly considered as sort of a first lecture about this subject. If you are learned from, for example, computer vision or NLP, maybe this is what kind of unification of all the things that you have studied. So it still might be very good for you to really sort of go through this material. And also this serves as very good sort of tools for you, later on to come in with algorithm, right, to solve some of the games. You can actually solve some of the more complex multi-agent problem. You can actually making use of, for example, embedding, for example, using convolutional neural nets to create your policy, or you can make use of some of this latest self-supervised learning for your decision-making problem. So after today's lecture, and we will have a reading week next week. And when you come back, we will talk about decision making, right? So these 4 are more game theory, right? We're talking about these Nash equilibrium interactions, and this we started today. We talk about learning, right? The learning, and then we talk about decision making. We might sort of swap these two, just to make sure that you could have a quicker understanding about this multi-agent learning once you understand the single agent learning. And so once you got this game theory stuff, this learning, then plus these two together, we can actually tackle a lot of the exciting problems that we're going to introduce after reading week. So in terms of the syllabus, do we have any questions? Okay, cool. So definitely you need to make sure the picture, right? The big picture about this module, so that you don't really lost. Otherwise, sometimes you might confused. Why we need to talk about the convolutional neural network today? Why we need to talk about this, Bayesian game? There's a reason behind it, right? I think for the later, more complex sort of agent interaction, you do need to know the. In some of cases, you don't really observe everything, right? Therefore, you need to build that kind of Bayesian inference view of the problem, and so on and so forth. So the question here is why we need to learning anyway, right? So we were talking about agent or players. Then these AI, think about this AI, and in the most of cases, in fact, it's about individual agent or individual system, although they didn't really say that, but it's actually is a individual, this individual, I don't know how to call it, either called a system, right? Or is it called a certain combination of that system, but they are go through all these past experiments. Based on this past experiments, they can actually make a prediction, and they can improve their functionality. So this is sort of what machine learning is really about. And then this AI unit itself can act as sort of agent. Therefore, they can perform those learning tasks. Therefore, can improve when they experience more data. So, in this kind of setting, really the goal is for us to design kind of this intelligent unit, what we call the agent, is that they in fact is try to learn a function. Okay, so this function can be somehow can map between their current context or their environment, and would be able to perform action. So this action could be classification, right? In the typical machine learning task, or be some other kind of task, and then they will receive the payoff. And the goal for that is try to come in with a function mapping, right, from the state to the action. And then there's a function in between is really to construct that kind of mapping. So let's say the function. So you can actually think about the learning. Most of learning problem is really about that. You could got the state, and then it's sort of a parameter of that function that provide this sort of action. So the goal is then become these machine learning or this learning a single agent is really about to come in with this function, this optimal function, so that at right time, given a right context, I will make a right action. So another example would be like say I try to predict the click-through rate of a user. Then the state would become contextual information would become sort of a, let's say, user periods behavior, right? User periods behavior. We could do the X and X1 or X user. And then we can also this item, the item could be a particular web page, right? And this, when the information all given, then we try to predict the action would be straight, whether 0 or 1. User likely being clicked on that or not. So this become sort of a classification problem. I want to class the user item pair into, they're going to have a click or they don't have a click. So you can you make using a various way to construct this function, right? The theta to represent parameterize this function. So I think a simplest one would be, I think that you probably know in other modules like a logistic regression, right? You come with a simple representation of the function to perform that prediction. So, and no matter how complex it is, in the end, the underlying, fundamental problem is solve this mapping problem from your current context to your action. So the AlphaGo is the same thing. I think this is one of the these oldest slides about AlphaGo that's sort of ranking 4. But in fact, obviously now is that better than any human being in terms of play chess Go. So in this case, you can think about same thing is that I got a state, which is, this what's current in the current game. And then I would need to have a function, given this as input, I will actually produce, the action. So that the action is optimal. The action would be say, do I paste this white here, or do I paste this my stone here or not? So the interesting things, I think, if you know the history, is that back into, let's say, 6 years or so, or maybe even earlier than that, people find that if you have a not just logistic regression, right? If you have a neural network, put everything together, make it deep, you can solve a lot of problems. Like people at that time, people reported the progress on various of speech translation tasks. Find that if you're using deep learning, deep neural network as a function approximator to approximate the function that I mentioned for let's say in this case, a machine translation task, I can find that that's a great improvement. Same case with computer vision, right? Started with that, Google doing this sort of unsupervised learning, and also this various of classification tasks like ImageNet. For example, the success of convolutional neural nets, which is also deep learning network. And can find also, I think this was 2015. And then at that time, you already bypass this human level sort of classification performance, and you're looking at this layer, like this earlier stage of neural nets, right? In 2012, 7 layers, 22 layers, 152 layers, and now 1,000 layers, even more. And these improvements, this is what I get yesterday. And if you're looking at this ImageNet nowadays, and so by the way, so for this, these are the top 5 accuracy. So when I say this these sort of errors or this accuracy, they are these top 5. So meaning that for each of label, as long as my predictions are around this 5, then I will be fine. So as long as my top 5 predictions is, if one of them correct, I will be correct. So this is evaluation. But here, you can think about this top 1 accuracy is already, 90%. And in terms of top 5 is already like a 98%. So here is, I think it was much lower than that. So this is a state of art, and obviously a lot of various of techniques, but the underlying is the neural nets. So same case with NLP, natural language processing. People start with word embedding. And this embedding is very impressive because when you're using sort of a so-called distributed representation, which is nothing but using a vector to represent each of the words. And you can find that they have certain semantic relationship. If you plot that in this, this high dimensional space. In this case, it's using sort of a low dimension projection into 2D. But as long as you have this vectorized representation, and then you can find this, there's a semantic meaning behind it. And again, if you're looking at the latest result, again, copy paste this morning from this super glue benchmark, which benchmark a lot of language related tasks. They basically using some of these deep learning to do representation learning. In other words, have a multiple layer neural network to try to come with a better representation. So this is beyond word embedding. I do this transformers, but and everybody heard this GPT 2 on GPT-3. So you can find that also. So this is human baselines, and you can see that also make a substantial improvement. So same case with the control that I mentioned. So then what is deep learning anyway? So deep learning is really nothing but a neural network, right? But you just have a multiple layer of that. And I can very quickly go through the history. So in the very beginning, is that people started with perceptron, which is one layer neural nets, single layer neural nets. And at that time, I think in 60s, people actually realized the perception, although very good, can solve some problem, but they have a strong limitation. They're not even able to solve this nonlinear classification problem. And become sort of people become very despondent about that, and many people research on neural nets, so they basically left that field. And the second wave starting in the 80s, then these rediscovered, I would say, because a number of people proposed the same idea many times, and so it's basically say we have this quite efficient algorithm, backpropagation algorithm. And for when you have a multiple layer, let's say 2 layers, and then you can actually have a way to learn these 2 layers of neural network or 3 layers. And the people started to do the research again because they can do interesting things like face detection, so on and so forth. And the third wave is what we have happening now, is that from 2006, people find that if you stack all this neural network together, you can find that it can solve a lot of interesting things. So my talk would be actually have this presentation learning as well. So I'm going to talk about a bit on neural network, how backpropagation works, and we will go through all these latest techniques you might be able to use, right, for multi-agent learning. And after that, I will quickly go through this monocolor tree search so that you can have a reasonably good understanding of how AlphaGo works. So neural network is this is a biological neuron, and people basically brought the idea, create this very simple neural network. Think about this. You have suppose you have a vector as the input, and then basically weighted average of those features, and then have this let's say a bias terms, and then you apply this nonlinear kind of transform and into sort of a binary case, let's say, then you do a lot of classification. So think about this, that remember we have a function. So this function can be replaced by, this neuron, simple neuron. The input is X, right? The output is Y. Think about this X, it could be the context information that I mentioned. And Y would be sort of your decision or your, prediction, whatever machine learning task you would able to have. And this W, M, and B is the theta we just mentioned, right? These are the parameters that you learn. And so at that time, and people think about this even before like a personal computer, the big computer invented. So people were very excited to think about this is AI. This is the future of AI. Just like what we think about now, think about deep learning is AI, can solve all AI problem, but actually it's not. So these layer, and then at that time they come up with a similar to backpropagation, right? But obviously just one layer. You can update this. They have a simple update rule to update this parameter. Okay, based on I give you like a X input X and Y. I'll give you, a pair, right? Multiple pairs, and they can actually use the training data to learn this WM, and therefore you can solve some of the problems. And like for example, if you're a linear classification problem, you can actually learn this W1, W2, and B to separate this class 1, class 2. So you can look at the update here is quite similar to these backpropagation one we have. It's actually the same. But if you're looking at nonlinear problem, if this, let's say two class classification problem, let's say these are the negative class, this is a positive class. You can't separate them by just one hyperplane, or this in this case a line. If you encounter this problem, then this simple perception wouldn't work. But you can actually make use of 2 layers, right? Let's say you got this hidden layer. You project that into a different space. Think about that. Or you project into a space that can separate them. Or you can think about is that I have multiple classifier, right? I can multiple linear classify. Each of them draw a line in this decision space, and then combine them all together, and then I can actually classify this. So then it give you 2-layer neural network. But obviously, this network structure is not unique. You have arbitrary way of doing it. So for example, you can come up with sort of this kind of structure is this kind of structure, and then you can separate them. So this paper, in fact, lists quite a lot of way to do that. If you're interested, you can have a look. So and then when we move to the 80s, and people, as I said, we have efficient solution for this 2 layers network. And then people are really put a lot of effort on this so-called 2-layer feed-forward neural nets. We should think about each like this is really nothing but, let's say, one perception, and then you got another perception. And after these 2 hidden layers, you combine them together, create an output. So then you can do is that you can still have this like a X and Y pair, right? So you have your X input and you have this sort of Y, your prediction, given this certain parameter, and you have this ground truth Y. I can using this sort of errors between your prediction and also ground truth. Because think about this prediction, you can actually write it down as a function, let's say neural network input plus a parameter. Okay. So you can backpropagate, make use of the error. The goal is try to minimize this error. So I would choosing the theta in such a way so that my y prediction would be as close to these ground truths. Therefore, I can create this algorithm, can update, right? I can update. This update would really based on this error that I created. Try to minimize the error. So, and once you have that, you can using a lot of make use of this for a lot of interesting problems. So this was when I was a master student, like you guys, and I did sort of master project on this using neural network. That's how it's not really deep, only 2 layers to classify faces, but I didn't work on that pixel level, but we'll work on this compressed domain. The idea was saying that given these like IPAC data or JPEG data, I don't need to compress them. I just using those low DCT sort of in the frequency domain and try to recognize the face or not. So I think that was idea we had. So obviously we look at it now, it's probably not really good idea, but at that time I think that the computation is very critical, but now we don't really think decoding unpack is something difficult computationally. So this is sort of result that we as a student got that. So this how it works, and as I said, you got this output, and then you got this ground truth, let's say, and this is your output from the neural network, let's say y hat, this is y. And you got the error, and using that to propagate it back to the neural network, and therefore can update neural network later. Let's see how this works. Feed forward is easy, right? You got this X and you weighted average, and using weighted average and then using this sort of a nonlinear function, then you can compute this value in the hidden level layer, and then combine all this hidden value from the hidden network, and then again using this nonlinear function, and you make your prediction. And yeah, make a prediction. And then when you try to learn the parameter, what you do is that you got this error, right? You got this your y here is basically your sort of prediction. The d here is y, the ground truth. You got this rare error, and this error can propagate back. And what you do, in fact, you can just a little bit of math on take a derivative of this all this weight, right? And it turned out that derivative over, these, because the derivative basically over this y, the predicted value. This y is dependent on, because of this weighted average, and then uses the nonlinear function. In the end, you will get this is take a derivative of this function, and also this this edge is basically the input to that backpropagation value, which is basically one of these edges. Because you want to say, I want to update this W, right? The rest of the other W, basically, I can is 0 when you take a derivative. But we take it because it's linear, right? With respect to that, therefore you keep the F here. So then you can have this very common sort of formulas for this delta W change. Right? The eta is learning rate, and you add the error propagate back from the previous layer, and also this output from you from basically it's actually input of this value. Of this error here. So you could do that for this layer in the output layer, but also you can do that for this input layer to backpropagate that. So you can. This is a very easy way, and in fact, even TensorFlow or something, you don't really need to worry about that, right? Because the code would help you to do that backpropagation. So here I just give you an example to make sure that although you can now using these tools, they can automatically calculate for you. But I think it would be good that in fact you can manually done yourself. Just make sure they absolutely understand that. So I think this gives you a good example for you to go through it in terms of calculation. And then there's various of an activation function called active function, and this is a sort of property of that. So I'm gonna pass that. You can have a look on various of a function. There's some property of that, like a ReLU function being heavily used that is got quite nice property that can have this spice representation. So this is sort of activation function. Also, this lost. You can come up with all kinds of loss. For example, I just mentioned this mean squared lost. You could also have this so-called cross entropy or the softmax lost as well. So this sort of backprop, most of those backprop require you need to have a training data. In other words, you need to have a labeled data to give you the error so that you can backprop this error. So if you have a manual layer, that might be a bit slow, but also from the optimization perspective, this is called convex optimization, and they might stuck to the local optimal, so never be this optimal solution. So people from the optimization viewpoint, globally, they not necessarily give you a optimal solution, but somehow make this deep learning quite efficient for now. And so there's a lot of theory behind, like a theory of deep learning. Turns out, try to understand why deep learning can generalize quite well, and also can not easily overfit to the data when you have a large amount of parameters. So there's a lot of theory behind it. So I think that's also quite active research now in terms of really to understand backpropagation, also the deep learning itself.